Hey guys, I want to talk a little bit about alternating series. I want to take something back that I said in my upstairs class at some point last week. So this is an alternating series, right? Because we have this piece that we sort of think about controls the sign, right? Or it oscillates between positive and negative. And then here we have our sort of actual a sub k, right? And we looked at this series last week and we said, how do we prove that it converges? So to prove that this thing converges, we had to show two things. We had to show that the limit is as k approaches infinity of these a sub k's equals 0, and we had to show sort of that they were decreasing, or getting no bigger at least, right? So the first part was pretty easy, right? We can easily see that that the limit as a sub k, as k goes to infinity of a sub k is 0, right? Because we have k on the top and k squared on the bottom. So this part is sort of easy, right? This is easy. The second part, I was talking about a limit the other day, and I want to take that part back, okay? So we said that if, to show that a sub k is greater than or equal to a sub k plus 1, we can divide by a sub k. And we can sort of show that a sub k plus 1 over a sub k is less than or equal to 1. Okay, and I was looking at a limit, but we don't need a limit, and actually we can't have a limit. So I want to take all that back, right? Everywhere there was a limit there, because we need this for all k, right? So we aren't looking at when k goes to infinity. I mean, we are, but we also need it for all the k's in close, right? Where k is 1 and k is 2. So we're not only concerned with the end behavior, we're concerned with all behavior. So what we should have done is we should have looked at this expression. All right, so we know that the k plus first term of our series is going to be k plus 1 plus 3, right? Over k plus 1 times k plus 1 plus 1, right? That's sort of that first term. And then over a sub k, right? So this guy, I'll just write this is a sub k plus 1 up here, and then this will be a sub k. And a sub k is just k plus 3 over k times k plus 1. And while we could simplify this thing, and we did this with sort of a limit floating around, but let's undo that right now. So that would be k plus 4 in the numerator over k plus 1 times k plus 2, right? And that would be times k plus 1 over k plus 3, because we're multiplying by the reciprocal of the guy down here. Okay, let's look at what cancels nicely, right? These k plus 1s go away, and I'm left with something that looks like this. Same thing we were left with in class, but again, without the limits. K plus 2, k plus 3. And so this thing is just k squared plus 4k over k squared plus 5k plus 6. And that made us pretty happy, right? Because we sort of have this notion that the bottom is going to be bigger. But why can we say that, right? Well, we can say that because k is always a positive integer, right? Maybe if k were negative, right, these things might interact a little bit differently here. But we don't know. We do know that k can't be negative, right? So sometimes you'll see books rewrite this like this. That's a bad 2. All right, all we're doing is sort of separating that. And then we have this thing here where I have the same thing in the numerator and the denominator, and then something that's definitely positive over here in the denominator, right? So we know that this thing is less than or equal to 1 for sure, even as we go off to infinity and in close, right? So this is sort of the proof that we want to say, right? Because k plus 6 is greater than 0, right? And we know that's always true. It's really greater than 6 all the time, right? Because k plus 6 is greater than 0, a sub k plus 1 over a sub k is less than or equal to 1. Right, so that's what proves it, not a limit. This is what proves it. Okay, and then we are going to start talking about this idea of conditional and absolute convergence, okay, which might be kind of tricky, but you're going to need that for your homework due for my upstairs class. That'll be Monday, yeah, the day after your test. Okay, so let's think about this idea, and let's suppose that I just have some generic series. Okay, so this is sort of review from my downstairs class, my upstairs class. We didn't quite get here, right? So let's just think about some general series, and let's suppose that this guy, so we should say suppose that this thing converges. Suppose that thing converges, and let's say all a sub k's are positive. All a sub k's are positive. So we're dealing with a positive series here. What would we know if that thing converges? What do we know about this guy here? What do we know about this guy here? Sorry, not what do we know if I have the alternating series of these terms? What do I know if I take those terms and I alternate them? Well, if all of these terms up here in this red guy are positive, right? And then I subtract some of them, right? I know that my green series, right? We know that this green guy is strictly less than or equal to that other guy, right? I know that this is less than or equal to the red guy because all of these terms are sort of pulling in the same direction in the red guy, right? They're all positive. We're summing up a whole bunch of positive things. In the green guy, some of them are negative, right? So it definitely can't be as big. Maybe all the terms are 0 or something in a silly series, and then then this equality would hold, right? But at best, right, they're equal, and more likely than not, the green one is actually smaller than the red one because some of the terms are negative. So what do we know about this thing? We know that it converges too. That it converges also, right? And if you need some convincing, we can say this converges by the alternating series test. Okay, let's think about why that is. Okay, I'm just gonna sort of sketch this out verbally rather than writing anything down. Well, if the red series converges, right, that means the terms are going to 0, right? That means the terms are going to 0. If they weren't going to 0, it wouldn't converge. So that means the green series will also converge. Okay, that's good. Sorry, not the green series will also converge. That means the green terms are also going to 0, right? If the red terms are going to 0, the green terms are going to 0. Okay, and then we know that if the red terms, right, if they're converging, right, they must be getting smaller at some point, right? They must be getting smaller at some point, because if they weren't and they were getting bigger, right, then they wouldn't converge either. So we have the same property for my green a sub k's, right? They must also be getting smaller because the a sub k's are the same. The green one, just we're multiplying it by -1 some of the time. So we know this converges by the alternating series test. Okay, and we say that the green series, this guy, the green series here converges absolutely. Okay, or we could say absolute convergence. And those are the two sort of forms you'll see that in. Absolute convergence, okay? And we sort of define that, we say, in an alternating series, if the absolute value of the terms converges, then the alternating series converges absolutely. Converges absolutely. Okay, and what does that mean again? That means if we ignore the oscillator part, right? If we ignore this part and it still converges, then it converges absolutely. Okay, so this might seem very silly, right? Like, well, of course it converges absolutely, right? What other types of convergence are there? Well, we looked at this crazy series, right? We looked at our harmonic series. Our harmonic series, this guy, k equals 1 to infinity of 1 over k, we said that diverged, right? That diverged by the p-test, where p is 1, or diverged by the integral test, where we took that integral, right, and that became ln, and it marched off to infinity, right? So this guy diverged. But we saw in class the other day, I think we did 1 over 6k maybe, we saw that this series, doesn't matter whether we have k plus 1 or k up there, right? That this series converged. So here is an example right here in red of the alternating series, right? Where while this series converges, the alternating series converges, if I took the absolute value of every term, right? That would be ignoring the -1 oscillator, right? Because we're looking at the absolute value. If I ignored the oscillator and I took the absolute value of all the terms, it would diverge. So the alternating harmonic series converges, but the absolute value of the terms, and that's the regular harmonic series, diverges. Okay, so we would still say that the alternating series converges, okay, but we would say therefore the alternating harmonic series converges conditionally, meaning again, its absolute value does not converge at all. So we'd say it converges conditionally, as opposed up here we said that other series converged absolutely. Okay? So we have this two different types of convergence for these alternating series. We have conditional convergence and we have absolute convergence. And to show absolute convergence, right, you have to show that the alternating series converges, and you have to show that the absolute value of the terms converges, right? And we're sort of going to be able to get that if we just show the absolute value converges, right? Similar to our argument up here, well, if the absolute value of the terms converges, then the terms converge themselves, right? So we can sort of ignore that part. To show something converges conditionally, right, we have to show the alt series converges. We have to show the alt series converges and show the absolute value of the alternating series diverges, okay? So you could use the divergence test or something else to show that those things diverge, okay? So we're going to need to know that in order to do our homework, okay? So that's what you're going to need to look at. You're going to need to look at the series with these oscillators and be able to say something about them, and then without, and then based on what that does, you should be able to do some problems and sort of assign whether they are converging absolutely or converging conditionally. And then we had this thought question: could an alternating series diverge, but the absolute value of the terms, could that converge? Do we think that's possible? Could an alternating series diverge and go off to infinity Well, if I took the absolute value of all the terms, could they converge? Do we have a sort of a conditional divergence? And the answer is no. And we will discuss this on Monday. On Monday, right? We have absolute divergence. Oops, mixing up my ordering here. Absolute divergence, right? And in keeping with our theme of class, both of the series, let's say alternating and absolute value, both diverge, right? If they both diverge, we have this absolute divergence. We don't really have conditional divergence because this question up here, this guy, is not possible. Not possible. Okay, so there are a lot of words here, and not a whole lot of examples. So maybe we'll think about some for our homework, and we'll think about some for our for class on Monday. If we wanted to think about an example, right, we could think again about our harmonic series friends. So maybe I'll look at an example of something similar to that we saw in class maybe. So let's think about 1 over we'll do 2k. Okay, let's think about this series times some oscillator. Okay, so we could easily list the terms here. If I wanted to list the terms in blue, right, the first term when k is 1 is going to be 1/2, right? And then the second term is going to be minus 1/4, and then plus 1/6, and then minus 1/8, and then plus 1/16, not 1/16, 1/10, 1/10, okay? Minus 1/12, dot. We get the pattern, okay? So that's what that series is going to look like, okay? And we could show a number of things, okay? We're going to show that this thing converges conditionally. So again, to show absolute convergence, look at the absolute values, right? And again, if the absolute values and show convergence, any of the ways we've seen so far, right? The ratio test, the integral test, whatever you want, geometric series, any of those, okay? You have to pick the right one for the series in question, right? But we can look at the absolute value and show convergence. To show conditional convergence, we need to do two things, right? Absolute values diverge, and two alternating series converges, right? Those are the two things we have to show. Okay, so let's start with 1. 1 is sort of easy. Show that the absolute values diverge. So that's just saying ignore those other things. So we're considering this series. We're considering 1 over 2k, right? We ignore the negative 1 to k plus 1 because that thing's either just 1 or negative 1. And if we're taking the absolute value, it's always 1. So we're considering this guy. Well, we know obviously either by the integral test or the p-test, right? We could say this thing is really a half times this sum, right? And we know by the p-test, right, with p equal to 1, right, so there's an imaginary 1 up there, but by the p-test with p equal to 1, this thing diverges. Right, that thing diverges. So we show that the absolute value guys diverge. Now let's consider the alternating series, okay? So now we're considering our original problem. We're considering this guy here to prove that it converges conditionally, or some of the time, right? So how do we show that this thing converges conditionally? Well, we have to show two things, right? Again, we have to show that the limit as k approaches infinity of the a sub k's, remember, the a sub k's are really 1 over 2k in this thing, right? It's the non-oscillating part, equals 0. And we have to show that nonsense where they're all getting smaller. Right, all getting smaller. I don't know why I keep on drawing a comma there. Okay, so let's show A. Well, does the limit of, as k goes to infinity, of 1 over 2k equals 0? I don't really need to show anything for that, right? We did that in TIC or AB Calc, right? We're very good with this, right? We're very good with this. Of course it does, right? The bottom's getting big, the top is staying at 1. So, of course, this approaches 0. Done. Okay, B again, we don't want to look at a limit. We want to look at the k plus first term over the kth term. And can we show that this thing is less than 1? That's the goal, or equal to, right? So can we show that the k plus first term is 1 over 2k plus 1. And the kth term is 1 over 2k. Well, that's really just 1 over 2k over 1 over 2k plus 2. I have no idea why I just wrote it like that. That is not at all what that is. Oh, sorry, brain fart here. Right, that is 1 over 2k plus 2 times 2k over 1. What on earth just happened to me? Okay, I think I just reversed the fraction and took its reciprocal. Okay, so forget that ever happened. Okay, so we have this thing here, right? And this thing is just 2k over 2k plus 2. Okay, and because k is always positive, right? K is always positive. The bottom always bigger by 2. Always bigger by 2. Okay, always bigger by 2. And therefore, this thing, right? This thing is less than 1. Therefore, it converges. The alternating series converges. And then we would say, because this guy diverges, right? Sometimes to be more exact, you might see it written out nicely like this with absolute value bars. Diverges and this thing converges, right? That first series that we looked at, this guy, 1 over 2k, negative 1 to the k plus 1, converges conditionally. All right, so excuse that disastrous moment where I, wrote something that wasn't true up here. It's good now. And hopefully you'll be able to listen to this and then do some homework over the weekend. Enjoy that process. Awesome.